Welcome to True Projects. In this video, we are going to explain about the project that is a comprehensive analysis of machine learning algorithms in IoT IDS systems. Before getting into the execution, first let us understand what is the project about. The Internet of Things, that is IoT, has really changed the way we live, allowing devices to communicate and share data in ways that were unimaginable just a few years ago. Think about smart home devices like thermostats, security cameras, and even fridges that can connect to the internet, or how IoT is revolutionizing industries like healthcare and manufacturing. It is amazing how these devices make our lives easier, safer, and more efficient. But with these all advancements, there is also downside. As more and more devices are connected, they create a much larger network, and not all of these devices have strong security features. Many IoT devices are vulnerable to attacks because they don't have the necessary protections in place, which opens the door for hackers. These cyber attacks can have serious consequences like stealing personal data, disrupting business operations, or even causing financial loss. This interconnected nature of IoT only makes this problem worse. When one device is compromised, it can give hackers access to other devices in the same network. So while IoT has brought a lot of innovation, it also created new security challenges that we need to address to protect our data and systems. As IoT networks grow, traditional security methods aren't just enough anymore to keep up with the new kinds of risks we are facing. IoT systems generate huge amount of complex data that's often unstructured, which makes it really hard to manage and secure with old school methods. We need more advanced techniques that can spot unusual activity or anomalies and accurately identify different types of cyber attacks. The scale of IoT networks means we can't afford to have slow, outdated security solutions that only catch some problems. They need to be scalable and flexible enough to handle threats in real time. So, this is crucial because if an attack happens, we need to detect and respond it to immediately to protect the system and prevent sensitive information from being stolen or compromised. Essentially, securing IoT networks means developing smart, adaptive solutions that can handle the volume and complexity of threats while keeping everything running smoothly and safely. This project is designed to improve the security of IoT networks by building smart intrusion detection system by using machine learning algorithms to spot and stop cyber threats. It takes look at different ML algorithms. So here we look into different algorithms that are naive Bayes, KNN, XGBoost, random forest, and logistic regression, and test them on four different data sets that are UNSW NB15, IoT ID 20, CIC IDS 2017, CIC IoT 2023. And these data sets are full of both normal network traffic and also potential attacks such as DDoS, Mirai, reconnaissance, and other IoT attacks. IoT specific threats giving the system a good variety of situations to learn from. So, to make the system work efficiently, we have gone through some pre processing steps like scaling, normalizing, and also we have selected important features using ANOVA technique. After that, the system measures how well the algorithms are performed. So we use accuracy, precision, recall, and reference code to evaluate all the algorithms built in this project. Moving on to the extension part. To further improve the accuracy, we have incorporated the ensemble based method that is voting classifier. What this does is it combines the predictions from three different machine learning models to make a final decision. Think of it like getting multiple opinions before making an important choice. By blending the strengths of these models, we get a more accurate and reliable result, which makes the system stronger overall. On top of that, we have built frontend using Flash framework, which allows users to interact with the system. With this frontend, users they can input data, get predictions, and review the results in a user-friendly way. We have also added user authentication mechanism to ensure that only authorized people can access and use the system, which adds a layer of security. This makes the intrusion detection system not only more practical and effective, but also more accessible and secure for anyone who want to use it. Moving on to the implementation of the project. To implement this project, we have followed the steps in the flow of work. So first, we start by importing the necessary libraries and packages required for data analysis, machine learning, and web development. Then we load and explore multiple data sets that are IoT data sets, which are nothing but CIC IDS 2017, CIC IoT 2023, IoT IT 20, and UNSW NB15 to understand the structure and contents, focusing on attack and benign traffic. So we will be loading all the data sets and we will be exploring so that we can understand all the data structures in this data sets. Then we pre-process the data where we clean the data set by removing any duplicate entries to ensure model isn't biased. Then we eliminate unnecessary or irrelevant features that don't contribute to the prediction, and we normalize the data to ensure all the features are on same scale for better model performance. Then we visualize key data patterns to understand the relationships between features and identify any trends or anomalies. After that, we convert categorical data into numerical labels so that the machine learning models can process them. After that, we use ANOVA, that is analysis of variance, to select the most relevant features, improving model efficiency by focusing on important data points. Then we split the data into training set and also validation set. Training set is used to train the model and validation set is used to evaluate the model's performance. Coming to the next step, we build the models. Here we initiate multiple machine learning models and then we train it on the training data set to learn the patterns in the data set. Then we evaluate using accuracy, precision, recall, and reference score, and we compare them using graphs. Coming to the front end part, we build a web interface using Flask, including a registration and login system that is supported by SQLite database to manage user authentication. Then in the front end users, they will be able to input the feature values, that is network related data for the prediction purpose, that will be pre-processed at the back end, that will be fed with the train model, that is the pre-processed data will be fed with the train model, and finally train model will be giving us the outcome, that is whether attack is there or not. If there is attack, it will detect which type of attack it is. Moving on to the algorithms used, these are the algorithms implemented in the project for detecting the intrusion detections, to detect the intrusions, that is the attacks. Coming to the requirements of the project, to implement, we need basic requirements, which are hardware and software. So coming to hardware, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. Now let us execute the project. To execute, open the code folder which contains source code files. So let's open the code folder. These are the source code files in the code folder of the project. Let us understand each of them. How will they be used in the project? So here in the CIC IDS 2017 folder, we have the data set. So this is the data set that we have used in the project. We will be pre-processing that data set, and this is UNSW NB. This is CIC IoT 2023, and this is IoT network intrusion detection dataset. So all these are pre-processed and they are saved as CIC processed, CIC IoT processed, and UNSW processed and IoT processed. Let us open one file. So this is the CIC processed dataset. Let's close this. Similarly, we have CIC IoT, UNSW, and IoT processed. Coming to the static folder, this folder consists of files related to CSS, JavaScript, and Bootstrap files that are important for the visual appeal of the project. And here in this templates folder, we have HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. In this model folder, we have the numpy files, .h5 files, and safi files that have the algorithm information in it. It will be loaded into the project code during runtime of the application. And here we have app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And here we have multiple Jupyter Notebook files. So here we have total 4 Jupyter Notebook files. So in these files, we have combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. So coming to this CIC IoT 2023 Jupyter Notebook file, in this Jupyter Notebook file, what we will do is we will be loading this processed CIC IoT 2023 data set, and then we will be training the models to detect the attacks. Similarly, CIC IDS 2017, here we will be training all the models on the CIC IDS 2017. Accordingly, IoT ID and also UNSW. And here in the sample files, we have the test cases that we will be using in the front end to detect the attacks. And here we have sign up file. This is the sign up file, which is used to store the user information. Now we have to copy the path of the code folder from the address bar of the file explorer to execute. So I'm copying the path. Now open the Anaconda prompt. So it has been opened. Now give the command cd followed by the space, paste the copied path. Now click on enter. If you observe, current directory is changed to the code folder's path. Now we have to compile the app.py file. So give the command python space app.py and now click on enter. So what will happen is this will compile app.py file and it will execute Python script and perform runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port unless configured differently. So now we have to copy this local link provided by the Flask framework and paste it in any web browser. I'm copying the link. I prefer Google Chrome, so I will paste it in that. Paste the link here, click on enter. And this is the web page of the project, which is displayed in the browser. And this is developed using Flask framework. So we need to register first. Click on register and enter all the registration details if you are registering newly. I have already registered, so I will directly sign in. Click on sign in. Give your username and the password. Click on login. We have logged in successfully and we are redirected to prediction page of the project. By default, we are redirected to CIC IDS 2017 detection. As we're doing multiple data sets and we have trained all these data sets for detection, individually we will be doing detection for all the data sets. So let's do first detection for the CIC IDS 2017. So click on that. Here we can see different parameters, right? We need to understand, we need to enter these parameters and then we will be getting the prediction. So let's understand them first. Initially, we had multiple columns. After applying feature selection, these are the extracted, these are the selected features. So let us understand what are these features. First, we have is the backward packet length maximum. That is the maximum length in bytes of a packet in the backward direction, that is from the destination to the source during the flow. It indicates the largest packet size observed. Coming to backward packet length mean it is the average length of packets in the backward direction across the flow, providing insights into typical size of the backward traffic. Coming to backward length standard deviation, this is the standard deviation of the packet length in the backward direction, showing how varied the packet sizes are in that direction. Coming to flow IET max, it is the maximum inter-arrival time between consecutive packets in a flow. This represents the longest gap in the packet arrival times. Coming to flow IIT STD, that is the standard deviation of the inter-arrival time for the packets in forward direction, showing how much the time between packet varies in a forward direction. Coming to forward IIT max, it is the maximum inter-arrival time between the consecutive packets in the forward direction, indicating the longest delay between packets. Coming to packet length mean, it is the average length in bytes of a packets in the entire flow, representing the general size of all packets in the flow. Coming to packet length standard deviation, it is the standard deviation of packet lengths in the flow, indicating how much the sizes of the packets vary from the average. Coming to average packet size, it is the average size of each packet in the flow, similar to packet length mean, but can also account for variability in packet transmission. Average backward segment size. It is the average size of the backward segments, that is the data sent from destination to source in the flow. Initial backward bytes. So these are the initial number of bytes in the backward window, typically related to the first data packet in the reverse direction during the flow. Then we have idle mean. It is the average idle mean between the packets in the flow, indicating how long the network remains inactive during the flow. Coming to idle max, it is the maximum ideal time in the flow, showing the longest period of the inactivity between the packets. Then we have as the idle mean. It is the minimum idle time in the flow, indicating the shortest time of inactivity between packets. So this is all about the parameters of CIC IDS 2017 dataset. Now let's enter the parameters. For that, we have to open the sample file. Let us open the sample file of CIC IDS 2017 dataset. So these are the test cases that we will be using now to detect the network attacks. And here we have multiple test cases, I mean multiple classes. Let's see what are the classes are, how many classes do we have. So total we have 7 types of attacks here. Let's check with one by one individually. So first let's check with the class 0, click on OK. So these are the test cases that we have for the class 0. Let's check with the test case 1 for the class 0, where backward packet length is 20. And the next we have is backward packet length information. So copy it, get back to the application, paste it. Backward packet length standard deviation is 5.30. Then we have flow IET max, that is 80 lakhs 60,000. And then we have IET standard deviation. Then forward IET max, packet length, copy it. Then we have is packet length standard deviation. Then we have average packet size, that is 778.3. Average backward segment size, that is 6.88. Initial backward win bytes, that are 256. Idle mean is 4,34,000, sorry, that is 43 lakhs 40,000. And then we have idle max and the idle min. So here we have entered all the parameters. Now click on predict. This input will be pre-processed at the backend and then we will be getting the prediction. So here we got the prediction, that is there is no attack detected and it is benign case. So that means that there is no attack found in the data that we have entered. Now let's try with the class 1. Click on OK. So let's try with the class 1 itself. Sorry, first case of class 1, where backward packet length is 6. Backward packet length mean is also 6. Backward packet length standard deviation is 0. And then flow IET max, copy the value. And then forward IET standard deviation is 4,372. And then forward IET max, packet length mean, and then packet length standard deviation. Average, then next we have is average packet size, that is 3. Average backward segment size is 6. 0 initial bytes and all the next values are 0. Now click on predict. So now we will be getting the prediction after giving the inputs. So here we got the prediction. Here attack has been detected and that attack is nothing but the bot attack. So here class 1 refers to bot and class 0, which we have entered previously, that refers to the normal. That means there is no attack. So here class 1 refers to the bot. Now let's check with the class 2. Let's enter all the values. So let's enter the values of first case. Here the first 3 values are 0. And let's copy the next 3 values, that are flow IET max, flow IET standard deviation, forward IET max. And the next all values we have is 0 except the initial backward bytes. So give the value 0. It's time to give the initial backward bytes. So let's copy that, paste it, and rest all are 0. Now click on predict. So here if you observe, attack has been detected and that attack is nothing but the brute force attack. Now let's try with the other class. So here class 2 refers to the brute force attack. We have completed 0, 1 and 2. Let's try with the class 3. Let's enter the parameters. Let's enter the first case. Copy the backward packet length. So here I have entered all the parameters. Now let's click on predict. And here we got the attack detected and that attack is nothing but the DDoS attack. So here DDoS attack has been detected. Now let's check with the class 4. So apply filter for the class 4. Let's try with the first case. So here the first backward packet length is 4344. So I have entered all the parameters here. Now let's click on predict. And here we got the prediction that attack is detected. Attack type is DDoS attack. Now let's check with the other classes. Let's check with the class 5. Click on OK. So of here the first case of class 5, I have entered all the parameters. Now let's check what will be predicted. Click on predict. And here we got the prediction that attack is detected and that attack is port scan attack. Now let's check with the other class. Let's check with the class 6. So here I have entered the last case of this data set. I have entered all the parameters. Now let's click on predict. And here we got the prediction that attack is detected and that attack type is web attack. So here web attack has been detected. Now let's check with the CIC IoT 2023 dataset. So click on that. Here we can see parameters, right? We need to enter all these parameters. So let's understand what are these first. So the first parameter we have is the protocol type. It is a specific type of protocol used in the network flow such as TCP, UDP or ICMP. It indicates the communication method between devices. Next we have is the duration. So this is the total duration in seconds of the flow, representing how long the connection lasted. Coming to the ACK flag number. It is the count of the ACK, that is nothing but the acknowledgement flags in the flow, indicating how many packets are part of the TCP acknowledgement process, typically used in confirming receipt data. Coming to RST count, this is the count of RST, that is reset flags, which are used to terminate a connection unexpectedly, often indicating an issue or deliberate termination in the flow. Coming to HTTPS, this indicates if the flow is using HTTPS protocol, which is a secure version of the HTTP commonly used for encrypted communications. Coming to TCP, this refers to the transformation, that is the transmission of control protocol traffic, a connection oriented protocol used for reliable communication in the flow. Coming to total sum, this is the total sum of all values for a particular feature across the flow, which could be used to summarize specific metrics like packet lengths or byte counts. Then we have is the min. This is the minimum value of a feature, given feature in the flow, such as smallest packet size, the shortest duration, or the lowest time interval. Then we have is the average. This is the average value of a feature in the flow, providing the mean measurement for the parameters like packet size, duration, etc. Coming to STD. It is the standard deviation of feature values in the flow, indicating how spread out or consistent the values are. Then we have TOT size, that is the total size. This is the total size in the bytes of the flow, representing the cumulative size of all packets transmitted during the session. Then we have is the magnitude. This is the magnitude of a value, that is packet size or a signal strength, typically representing the overall intensity or strength of the flow. Coming to radius, It is often used in the context of flow characteristics to represent the range or size of the flow's data, sometimes in relation to geographic or network parameters. The last one we have is the variance. This is the variance of the feature values, which measures the degree to which the data points differ from the mean, showing how varied the feature in the flow. So now let's enter all these parameters. For that, let's open the sample file of this CIC IDS CIC IoT 2023. So this is that one. And let's check with the classes here. So here total we have 7 classes. Let's try using class 0. Here, let's try with the class 1. Class zero's first case, where protocol type is 6, duration is 81.3, ACK flag is 1, RST is 795, HTTPS is 1, TCP is 1. The next value total sum is 1,222.6.5. Then minimum is 210.8. And the next value we have is average. Copy the average, paste it here. And then we have standard deviation. Then we are supposed to enter the total size, copy it, paste it here. Magnitude, radius, and the variance, that is 0.9. Now click on predict. This input will be pre-processed at the backend, and here we got the prediction. So here we got prediction is no attack detected. It is benign. So there is no attack detected in the traffic. Let's check with the class 1. Click on OK. Let's check with this case. So let's try with the first case, that is 8.83 is a protocol type, duration is 86.1, and 1 is the ACK, RST count is 246.79, and HTTPS is 0, TCP is 1, total sum is 1308.121, and minimum value is 58.84. And next we have is the average, that is 113.65. Next we have is the standard deviation, that is 89.61. And we have total size, that is 157.52. Magnitude is 14.77. And we have radius, that is 126.9962. And the variance is 0.91. Now click on predict. So here we got the prediction that attack is detected, and that attack type is brute force attack. So here brute force attack has been detected. Now let's check with the other class. So let's check with the class 2. So click on CIC IoT 23 again. Here protocol type is 17, duration is 64, ACK flag is 0, 0, and the next 4 values are 0. And the total sum value is 525. 50 is the min value. Average is also 50. Standard deviation is 0. And here magnitude is, before that we are supposed to enter the total size, that is 50. Magnitude is 10. Radius is 0 and variance is also 0. Now click on predict. So here we got the prediction, that is attack detected, and the attack type is DDoS attack. So here attack has been detected. It is DDoS attack. Let's check with the class 3. Let's enter all the values. So here protocol type is 6, duration is 64, and the next 3 values are 0, and the next one is 1. Total sum is 567, minimum is 54, average is 54, standard deviation is 0, and here we have magnitude value. Before that, enter the total size, that is 54, magnitude is 10.39, radius is 0, variance is 0. Click on predict. And now we got the prediction that injection attack is detected. So here class 3 refers to the injection attack. Let's check with the class 4. So we are supposed to enter all these values. Let's enter. I have entered all the parameters. Now let's click on predict. So here we got the prediction that attack is detected and it is DOS attack. So here DOS attack has been detected. Let's check with the two more classes that we have, that is class 5. Click on OK and click on CIC IoT 2023. Let's enter them. Here protocol type is 47, 64 is the duration, 0 is the ACK, then the next four values are also 0 and total sum is 6069. Minimum is 578, average is 578, standard deviation is 0 and the total we have is 578, magnitude is 34, radius is 0 and variance is also 0. Click on predict. So here we got the Mirai attack detected. So here Mirai attack has been detected. Let's check with the last class. Let's apply only filter to the 6. Let's check with this class. Sorry, we have clicked CIC IDS 2017. Let's click CIC IoT 2023. So I have entered all the details of all the parameters of class 6. That is the last class of this data set. Now let's click on predict. And here we got the prediction that attack is detected, that is web attack. So here web attack has been detected. We have completed all the predictions with the first two data sets. Now let's check with the IoT ID20 data set. Click on that. So here also we have the parameters. So first parameter is the source port. This is the source port number, which is a port used by the sender device to initiate the connection. This helps to identify the origin of the communication. Coming to DST port, this is the destination port number representing the port on receiver side that is used to accept incoming traffic. Coming to protocol, this specifies a protocol used in the flow, that is TCP, UDP, ICMP, indicating the type of communication method between the devices. Then we have total length of forward packets, indicating the cumulative size of the packet sent from the source to the destination during the flow. Then we have forward packet length max. This is the maximum length of a packet in the forward direction, that is from the source to the destination, showing the largest packet size sent. Then we have is flow IIT mean. This is a mean inter-arrival time between packets in the flow, representing the average time interval between consecutive packets. Coming to flow IIT min. This is the minimum inter-arrival time in the flow, which indicates the shortest time gap between the two consecutive packets. Coming to backward IIT mean, this is the mean inter-arrival time of the packets in the backward direction from destination to source, showing the average time between packets going from the destination back to source. Coming to backward IIT min, this is the minimum inter-arrival time in the backward direction, indicating the shortest time interval between packets sent from the destination to source. Then we have SYN flag count. This is the count of the flags in the flow which are used to initiate a TCP connection. A high count may indicate a SYN flood attack, a common DOS, that is denial of service attack. Coming to ACK flag count, this is the count of ACK flags which are part of the TCP handshake process to acknowledge received packets. A higher count shows more acknowledgement messages. Subflow forward bytes. These are the number of bytes in the forward subflow, which is the amount of data sent from the source to the destination during the flow, typically useful in the analyzing traffic volume. Idle mean. This is the mean idle time during the flow, which is average time period where no data is being transferred between the source and the destination, reflecting periods of inactivity. Then we have is the idle min. This is the minimum idle time in the flow, representing the shortest period of the inactive between packets or between bursts of the data transfer. This is all about the parameters. Now let's open the sample file of this data set. That is the sample IoT ID. So let's check how many classes we have here. So total 5 classes we have. Let's check with all the 5 classes now. Let's enter the first case of the class 0. Let's apply filter to the class 0. So these are the test cases of class 0. And here SRC port is 6235 and destination port is 19604, and here protocol is 6. 0 is the total forward packets. Forward packet length is 0, and the next value we have is 2656, 2656 and 2656. We have same 4 repeated. Let's copy and paste it. And here SYN flag value is 1, 0, and same we have here. Now let's click on predict. So here we got the prediction as attack is detected and the type of attack detected is DOS attack. So here DOS attack has been detected. Let's check with the class 1. Let's try with the first case of class 1. Click on IoT ID 20. So here the first 5 values we have is a 0. So let's enter the first 5 values as 0. And next we have 270s. And next we have the other parameters. All the rest parameters are 0. So enter the 0 values. Click on predict. Sorry, last value we are supposed to enter is the 70. Let's get back and enter the 70. Idle mean. So idle mean is 70. And here the last value idle min is also 70. Now click on predict. Here we got the prediction as attack is detected and the attack type is ARP spoofing. It is MITM ARP spoofing. Here attack has been detected, that is A MIT ARP spoofing. Let's check with the class 2. So let's enter the values. So here I have entered all the parameters. Now let's click on predict. And here we got the prediction that attack is detected, that is Mirai attack. So here MIRAI attack has been detected. Let's check with the class 3. Apply filter to the class 3. So we are supposed to enter all these values. Click on IoT ID 2020. I have entered all the parameters. Now click on predict. So here we got the prediction that there is no attack detected. So here attack has been not detected in the data provided. Let's check with the last class of this data set, that is class 4. Let's enter the first test case of this class. Here the port number is 52704. Destination port is 9020. Protocol is 6, 0. The next values are 0. And next 75, 73, 75, 73, 0. And here we have 010, 75, and 73. Now click on predict. So here we got the prediction that attack is detected and that attack type is scan attack. So here scan attack has been detected. So we are done with the all classes. Let's check with the last data set. Click on UNSW NB15. So here you can see the parameters, right? Similar to the past, all the data sets we are supposed to enter for this day. We need to enter all these parameters to this data set also. So let's understand what are these. First, we have is the rate. This typically refers to the rate of data transmission, such as packets per second or bytes per second, indicating how quickly data is being transmitted within the flow. Then we have STTL, that is time to live. It is a value that represents the number of hops and packets can make before being discarded. It helps to prevent packets from circulating indefinitely in the network. Then we have is the deload. This refers to the download traffic, typically indicating the amount of data received from the network or a remote source in a flow, often measured in bytes. Coming to SWIN, this is the sender's window size in TCP communication, which identifies the amount of data in bytes the sender is willing to receive before sending an acknowledgement. It helps in managing flow control. Then we have STCPB. This refers to the TCP sequence number of the source, which helps in keeping track of the ordered delivery of packets during the TCP connection. Coming to DTCPB, this refers to the TCP sequence number of the destination, indicating the acknowledgement or tracking number for the data received from the source. Then we have is the DWIN. It is the destination window size in TCP, which represent the amount of data the destination can buffer before sending an acknowledgement. It is used for flow control to avoid congestion. Coming to CT-SRV-SRC, this refers to the count of the connections involving service source pair, often used in flow analysis to track the number of connections involving a specific source and server. Then we have is CT state TTL. This indicates the state of connection combined with the time to live, that is TTL, which helps to assess the status of the flow relative to the number of hops left in the network. Coming to CT DST D port LTM, this refers to the count of connections to a specific destination port in the last time period, often used to track the frequent connection attempts to a particular port. Coming to CT DST port LTM, this refers to the count of connections involving specific source port and the destination port in the last time period. So, this is useful for identifying patterns in the port based connections. Coming to CT DST SRC LTM. So, this indicates the count of connections between a destination and a source IP address in the last time period, that is LTM, often used to track connections between specific devices over time. Coming to CT-SRC LTM, this refers to the count of connections from a source IP address in the last time period, that is LTM, used for detecting abnormal behaviors or attacks from the specific source. The last parameter we have is the CT-SRC DST. This refers to the count of connections between a source and destination in general, tracking the volume of data exchanges between two devices over specific time. So this is all about the parameters. Now let's enter these parameters. For that, open the UNSW file. So let's check the classes here. Here we have two classes. We just have two classes, that is the 0 and 1. Click on 0. Let's apply filter to the class 0 and enter all the values. So let's try with the first test case. Copy the rate. And then we have is the STL. Copy the STL. Then we have download SWIN, STCPB. Then we have is the DTCPB, DWIN, CT. It is next values we have is 2, 1, and all the rest values are 1. Let's enter all the rest values as 1. So here we got the prediction that there is no attack detected. It is benign. So here class 0 refers to the benign. That means there is no attack. Let's check with the last case of this project. That is the 1. So this we are supposed to enter. Here, give the rate where the rate is 1,25,000. 254 is the SCTL. Then next four values are 0. Then we have 24, 2, 24, 15, 24, 24. All the values are 24. Now click on predict. So here there is attack detected and that attack type is bot attack. So as of now, we have completed all the test cases for all the four data sets. So we have done multi-class classification and also binary classification. So for the first three data sets, we have done multi-class classification, and for the last UNSW NB15, we did the binary classification. Here, multi-class classification is nothing but we have detected multiple classes, and here in the UNSW, we have detected only the two classes, that is the benign and that is the attack class. So when we have when we have given the test cases for the multi-class classification, whether if the attack was detected, it will detect which type of attack it is, and if there is no attack detected, it will show that there is no attack. And coming to the case of UNSW, it will detect whether there is attack or not. That's it. Now let's check with the graphs. Click on graph. So here first we have for the CIC IDS 2017 graph. So here we have the data sets, graphs for the data set of CIC IDS 2017. These are the classes in the 2017. Here on x-axis we have all the classes, and on y-axis we have the count of each class. And this is the correlation matrix graph, which shows the correlation between the variables. And this is the accuracy comparison graph. And here these are all the algorithms are trained on this CIC IDS 2017 dataset on these classes for detecting these classes. This is the precision comparison, recall, and FN score. Similarly, we have for the CIC IoT 2023. So these are the classes. And here we have correlation, accuracy, precision, recall, FN score. Similarly, we do have for the IoT ID 20 datasets. So this is the sample outcome graph. Accuracy, precision, recall, and FN score. And this is UNSW NB15. Here we have only two classes. So that is why we can see only two bar graphs. This is two bar lines. And this is the correlation matrix, accuracy, precision, recall, and FN score. Now click on logout. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.